Yeah, it's got a fresh coat of paint, but it'll take more than that for this old gray mare to shine. Today on Engine Power, our 408 Windsor stroker receives a stout crankshaft and a set of race-ready slugs. So watch out, this old horse can really kick.
Whoa. Wow.
Engine Power has an awesome build for all you Ford fans today on a stroked Windsor. Now, if Fords aren't your thing, don't worry. The tech we're going to cover goes for any engine build. Now, the engine was used last year on a comparo show between a 6-liter LS and the 351 Windsor.
Now, for this chapter, we will be reusing all of the existing parts except for the rotating assembly. We will be increasing the cubic inches only to show what you can expect for torque and horsepower gains. But first things first, we're going to show you all the parts that were used the first time we put it together.
We started with a reman short block, then added a mild hydraulic roller camshaft and new lifters. Trick-flow 225cc high ports were bolted to the deck, chromoly push rods, an Edelbrock Performer RPM manifold was dropped on, and 1.72 ratio roller rockers sat on 7/16 studs. And once the engine was docked up to the dyno, a set of 1 3/4 dyno headers were installed and our quick fuel dyno carb supplied the gas.
Recently, our block received some massaging in-house to get ready for the stroker kit and new pistons going in. We used our mill and our cylinder hone, and here's a look on how we got the job done. The block was set up in the mill to clearance the bottoms of the cylinders for any stroke we want to run. So we put a generous 3/4 inch notch at the bottom of all 8 cylinders. From there, the block was put in our Sunnin SV15 hone. We had to remove 1/1000th of material from the cylinders for proper piston skirt clearance. We used a torque plate, which simulates the distortion of a cylinder when the head is bolted up. This ensures a round and straight cylinder for a better ring seal and a high-performance application.
Our jet washer removes a lot of the paint off the block when it's being cleaned, so we decided to change the color from black to Dupli-Color's engine enamel with ceramic in the new Ford gray color. Now that also gave us the idea to name this project Old Gray Mare.
The first step of the assembly process is to install all of the oil gallery plugs in the block. Some are threaded and some are press fit. Make sure to use a little sealant on the threaded ones and be careful not to over tighten them. They are a tapered thread and could potentially crack the block.
For power and longevity, proper bearing clearance is key. For an exact reading, a micrometer and dial bore gauge are the tools needed to get an extremely accurate reading. The first step of this process is to check the journal diameter on the crankshaft. You also want to check it 90 degrees from the first measurement to see how round the journal is. Now an upper main bearing is placed in the block and a lower one in the main cap. This will be the same journal location we just measured on the crankshaft. With oil on the bolts, the cap was torqued to 105 pound-feet because that's how it was done when it was a line board.
The measurement on the micrometer is the base setting for the dial bore gauge. When the neutral spot is found, zero out the dial on the bore gauge itself. When the bearing ID is measured, the difference will be the clearance we have between the crankshaft's journal and the bearing. This one has 0.003 clearance. This process will be repeated for all 5 journals.
Permatex Ultra Slick Assembly Lube is being placed on the bearings. It prevents scuffing and galling during initial fire-up by adhering to the component surfaces. A rear main seal is located on the crank flange, which makes it ready to be laid in the main saddles. Do this very carefully to avoid nicking the bearings or journals on the crank. It's an Eagle 4340 forged crank with their exclusive ESP armor finish. With the main caps in place, the same engine oil is used on the bolts that was used to check bearing clearances. We torque the caps to 105 pound-feet.
This crank has a 4-inch stroke and also has a 2/100 rod journal, so it will accept small block Chevy rod bearings. It has a 125,000th radius on the journals for added strength and has been internally balanced. This crank is rated to 1,500 horsepower.
Up next, a worthy crank deserves a worthy polishing. Plus, new rods and pistons to complete our stroker conversion.
Now that we have the capabilities to perform several machining processes in-house, we want to show you what goes on when you drop your parts off at the machine shop. Now, it takes large investments to acquire the tooling, the machines, as well as the knowledge needed to do the job and do it right. Today, we're going to show you what it takes to polish a crankshaft using the right tool for the job.
Having a crankshaft polished at a local machine shop should cost around $50. But if you want oil holes chamfered, the crankshaft cleaned, or any other crankshaft operation done, the price will obviously go up from there. Now, polishing will only remove a minimal amount of material. The idea is not to change the size at all, just to clean up what you have so you have a round, smooth, and non-tapered surface.
We use a Goodson 72-inch portable crank polisher and our MSC Vectrax lathe to polish our crankshafts. Now, there are several different grit belts available depending on what finish you want to end up with. Now, fine scratches can be removed with a 300 grit, but most crankshafts are polished with a 400 or a 600.
The rotation of the crankshaft in the lathe while we're polishing is very important because our crankshaft polisher's belt should turn away from the journal instead of into it. Therefore, we have to turn the crankshaft in the direction that it will spin in the engine while it's running, and here is why. Material on a microscopic level has to be laid back in regards to the crankshaft's rotation. Otherwise, it could cause some premature bearing failure if the crankshaft is polished backwards.
This is a 6-liter LQ4 LS crank that's in pretty good shape, so minimal polishing will have to be done. The speed of the crank's rotation is also important. We're going to turn it at 36 rotations per minute. This allows you to have more control over your progress. Turn it too fast and you can accidentally put taper in the journal. We're using a 600 grit belt to touch it up. This is done on both the main and rod journals. Let the weight of the polisher do the work. Don't force it by pushing down. When the belt is laid down, count the rotations of the crankshaft so it is even from journal to journal. Keep a micrometer handy as well. Checking them ensures perfection. Once we're happy with the 600 grit, we'll put on our 800 grit polishing belt. Now, this one looks aggressive but is actually designed to remove virtually no material. Adding a little crank polishing rouge will allow us to buff the crank to a mirror finish. The last order of business is to check the journals one last time with the mic. The end result is an impressive polish job any engine builder would be happy with. Now that you know the basics of how to polish a crankshaft, let's get back to the assembly on the old gray mare. Eagle 4340 forged I-beam rods and their new FSI line are being used for this build. Now, these things accept a floating wrist pin inside the bronze pin bushing. They come equipped with 7/16 8740 ARP rod bolts, and they use alignment sleeves for proper cap indexing, and the rod bolt is recessed to minimize the clearancing needed on the block. Now, they're designed to handle up to 800 horsepower and 8,000 RPMs, and they're a budget alternative compared to an H-beam.
A Mahle Powerpak piston kit was included with the Balanced Eagle rotating assembly. It utilizes the included 1mm, 1mm, 2mm low drag ring pack, and also comes with 927 wrist pins and wire locks. Up top, a 26cc D-shaped dish and dual valve reliefs. The same procedure that was used to check main bearing clearance is used to check the rod bearings. Our range is between 22 and 24 10,000ths. This one verifies at 23 10,000ths.
With lube on the bearings and oil on the piston and rings, we're using our Summit Racing ring compressor sleeve to install the assembly. It is tapered, allowing the rings to compress towards the bottom of the sleeve and make an easy entry into the bore. The low tension rings and slick cylinder bores make for easy piston installation on this application. No piston knocker was needed. Getting a little fancy there, aren't you?
This is a fancy wrench right here.
The stretch measurement came in between 44 and 46 10,000ths using our ARP rod bolt stretch gauge as per Eagle specs for the ARP 8740 fasteners. That was achieved with our torque wrench set at 74 pound-feet. Every one was checked, even verifying the last one, because that's the right way to do it.
She's there.
Nice. It went together really smooth.
Very smooth.
Up next, Pat checks the specs on that stroker, and he likes what he sees.
Hey, welcome back. Before we get started, we'd like to touch on a specific added element to this particular rotating assembly. The force it takes to turn it over is basically friction between the cylinder wall, the piston skirt, and the ring pack. But with ring pack and skirt technologies being advanced, plus different honing techniques, that friction has greatly been reduced nowadays.
Now, back in the day, a small block Chevy with a 5/64 compression ring and 3/16 oil ring pack could have as high as 45 pound-feet of rotating resistance. Now, we want to show you what this Windsor has with a 1mm, 1mm, 2mm ring pack, and it's pretty cool.
Since we have it, we're using our digital Matco torque wrench to measure the rotating resistance. This can be done with a less expensive dial torque wrench or an even cheaper beam style for the same results. This Windsor has an impressively low 11 pound-feet breakaway reading, and during rotation it maintains between 10 and 11 pound-feet. The lower the amount of resistance, the lower the amount of parasitic loss from friction. Now, this does not make any power, it just frees up what's already there. The rest of the short block will be assembled pretty quick. First thing to go back in is the camshaft. Duration at 50 thousandths lift is 236 degrees on the intake and 248 degrees for the exhaust. The lobe separation angle is 110 degrees. Lift at the valve with a 1.72 ratio rocker is 610 thousandths on the intake and 632 thousandths for the exhaust. Retaining it is a factory-style cam thrust plate. The TrickFlow billet double roller chain is in place, and it's time to degree the cam. We're reinstalling it in the exact same position as before, at 107.5 degrees intake centerline.
Now the ARP oil pump shaft and high volume pump are bolted on. The pickup is new. The reason is so we can run a new oil pan that has a location for a temperature probe to monitor oil temp when on the dyno. A Cometic pan gasket will seal up the new road race style oil pan. It's baffled and has an 8-quart capacity.
Cometic MLS head gaskets with a 27 thousandths compressed thickness and a 4060 bore will seal the heads to the decks. Our calculated compression ratio is 10.32 to 1. The heads are TrickFlow high port 225s. They have a 58cc chamber, 7/16 rocker studs, and are set up for a hydraulic roller camshaft. Keeping the head clamped in place are 1/2-inch ARP head bolts. They are torqued to 100 pound-feet.
With the 1.72 ratio rockers installed and lashed, Cometic intake gaskets and Permatex right stuff will allow the Edelbrock Performer RPM dual plane manifold to seal up the lifter valley. The same TrickFlow valve covers, with a different look, are capping this 408-inch stroker off.
I don't know if I can tell you how excited I am about this.
Watch the door. Oh wait, it's so wide we don't have to. Now we get to play in our new dyno cell and see how much this old mare improves on the power scale. Early model vehicles with a carburetor all shared a common problem called vapor lock. It's when the fuel inside the fuel line comes to a boil. Now it can cause hard starting issues as well as rough idling. DEI has an inexpensive solution to the problem. It's called Vapor Block, a fuel line sleeve made of glass fiber and polyester laminated to an aluminum outer layer. Now it greatly reduces heat in the line, which keeps the fuel cooler, so vapor lock does not occur. It's easy to install and available in 3/8 and 1-inch diameter sizes.
Up next, Cell Block D takes charge of its first inmate.
With our 408 Windsor stroker hooked up to the dyno, we're ready for our first run. Here we go, seatbelt on. I saw a number or two.
We're already above 500.
Wow.
Woo!
Oh my gosh.
How about that?
Oh my gosh.
Right now we're making 522 at 5,800, but look at the torque. I mean, we're square right now. We're 525-ish, same spot. Wow, carburetor looks good.
32 degrees.
And it's 32 degrees of timing. I have no idea what this new Piston's dish will take for timing.
1.28 horse per cube on pump gas and a dual plane manifold with a little cam.
Yeah, that's pretty awesome. And look how much manifold vacuum's in it.
Yeah, oh yeah, there's some restriction there for sure.
There's some definite restriction there. I am impressed.
Go put 1.5 degrees in.
I'm gonna go put some timing in it right now. All right, I snuck 2 more degrees of timing in it for a total of 34. Now we're gonna also change the RPM range, but not at this time. When you're dynoing, it's important to only make 1 change at once. Snuck a little bit more into it on the torque, I think.
This thing is awesome.
Our peak torque at 4,100, 530 didn't really affect power a lot. It made a 20.
Yeah.
Now that's going to be a function of the restriction at the manifold.
Yes. You happy with the timing where it's at? Let's just bump it up RPM.
I think let's bump it up RPM wise and go from there.
Here, you make the pull.
Oh, what?
You built it too.
Oh, that's what I'm talking about. All right. How do you run this thing?
I know better than that. Made a couple more, I think.
Smooth all the way through the pull.
Made a 22 at 5,800.
Yep, and that's about right, and still made the same torque, 530.
On the money.
Bam.
That graph's nice, man. It pulls good.
This is a nice little engine. If we fiddled with it more, we could eke some more out of it, you know. The biggest restriction that we can show right there is the air.
Yep.
Okay, so you have a 950 CFM carburetor on it, and at peak RPM, it's pulling 687 CFM. So what does that tell you?
Restrictions below the carburetor.
The manifold is the restriction, correct. And that's okay, because I think we have a good plan that we might step up the induction, and while we're at it, might as well step up the cam too. So this thing's lean and mean, man.
It is awesome.
This is a nice engine. Good job.
Yes, sir. For more information on anything you've seen today, check out PowerNationTV.com.
Recently, we paid a visit to Kazi Racing Engines in Winder, Georgia. If you're looking to make big power with a big block Ford, John Kazi and his team can help. They built us a 598 cubic inch engine that made 1,108 ponies and 933 pound-feet of torque. One of the featured pieces on this engine was the Kazi SR71 cylinder head, which was designed specifically for high horsepower applications. John shared his wisdom on the subject of cylinder head flow, and now we'd like to share it with you.
We're not real big airflow guys. We more like what we see on the dyno and the airflow, whatever it takes to do that. But some people that are really smart have told me that the airflow and fuel through this port is over 400 miles an hour. So let's think about that for a minute. It's pretty fast, okay? So there's a lot of mass going through there. Even dry air has weight. But what's in here also, 7% of it's fuel vapor. So it has a lot of weight. And when you have a larger cubic inch engine and there's 400 miles an hour worth of air and fuel going through it, it has to make turns. You know, in a perfect world it'd be straight, but you have to make it turn. And so the faster it's going, the harder time it has making turns. But at the same time, the speed is your friend as far as inertia and filling the cylinder at the end of the cycle and all that. So you don't want slow air, which would be a really big port with the same amount of flow would be slow air. Slow air is not going to continue to fill the port. So you have to have it fast in some places, slow in some places. On a head like this, fast down the middle of the port, when it goes to make its right turn down into the bore, it better get bigger, because if it gets bigger, it slows down and it can make the turn. It's like if you're in your car and you're driving down the road and you go to pull in a driveway, you don't speed up, right? The same thing here. So everything in there has weight to it. So it has, when it goes around a corner, it wants to throw the fuel out of the air if it goes too fast, because the fuel's going to go the long distance because it weighs more than the air. And if you have a port that's a little too small and you're trying to flow a lot of airspeed through it, big cubic inch engine, what we see happening is the air and the fuel can separate again. and then all of a sudden you'll have an engine where it detonates and it burns a piston up or something. You really don't know what happened, and you come back and you make the port a little bit bigger right in this one area, and all of a sudden it goes away. When you're making bigger cubic inch motors and you're trying to make advancements in the head, you want to make it bigger in the right place, but not so big that it slows the air down.
Well, John, I want to thank you for having us down and talking airflow and science and engine building. It was very much appreciated.
Thanks, it was a pleasure having you here.